So we're starting chapter 3. This is sort of the heart of our class, working with linear systems of differential equations, because they can model so much more than a single equation can if you have a system. And then we can build off of what we know about linear things to do nonlinear things, just like you can in calculus. Like you can linearize any function, and then you just work with a line, and it's a lot easier. All right, so first we're going to deal with a little bit of linear algebra. Yes. Oh, yeah. Sorry. Okay, so little mini linear algebra lesson. A vector is just a list of numbers or letters, usually written vertically, but sometimes they are written horizontally, like x comma y instead of x y vertically. And your book will often use that like when they're giving answers in the back as a way to save space. So be aware that happens. A matrix is just an array of numbers made up of column vectors. And the size of a matrix is described by giving the number of rows and then the number of columns in that order. So this matrix here, 1, 1, 1, negative 2, 5, 7, is a 3 by 2 matrix because there are 3 rows, 2 columns. So you would call that 3 by 2. To multiply 2 matrices, the number of columns in the first has to equal the number of rows in the second, and the product will have the number of rows from the first and the number of columns from the second. So that's sort of hard to remember, but if you write it out, a 3 by 2 times a 2 by 4, you can multiply 2 matrices together if their inner dimensions match. The inner dimensions must match, and then the answer, the result, will be the outer dimensions. So your result will be a 3 by 4 matrix. So the way you multiply 2 matrices is you take the dot product of each row in the first matrix with each column in the second matrix. So let's just, I'm going to multiply these 2 matrices, but I want to know what the result is going to look like first. So the dimensions of this guy are 3 by 2. And then this one right here is a 2 by 2. My inner dimensions match, right? The 2's match. And then my result is going to be 3 by 2. We're going to have 3 rows and 2 columns. So I like to just build my answer first. 3 rows. So 1, 2, 3 rows, 2 columns. So I just put in my blank so I sort of know what I'm supposed to get. Then you take each row of your first matrix, dot product it with each column of the second matrix. So I'm just going to look at my first row and my first column. If I take the dot product, that means multiply the first things together, multiply the second things together, and then add the results. Right? So I'm going to do 1 times 1 plus negative 2 times 3. Everybody familiar with the dot product? 1 times 1 plus negative 2 times 3. So, and because I was multiplying the first row times the first column, the result goes in row 1, column 1 of the answer matrix. So next, I'm going to multiply first row times the second column. First row, second column, so that should go in the first row, second column of the answer matrix. So I take the dot product of those, and it's going to go first row, second column. So it's going to be 1 times 2 plus negative 2 times 4. And just FYI, your graphing calculator can multiply matrices, and I can show anybody who's interested. But oftentimes your matrices or vectors are going to have letters in them, so your graphing calculator won't be particularly helpful. All right, so I'm done with row 1. right? I multiplied this 1, -2 by every column of the second matrix. So I move to the second row and start again. So I'm going to do second row times the first column now. So I'm going to take the dot product, 1 times 1 plus 5 times 3. And then stick with that second row, but go to the second column of your matrix. So that's going to be 1 times 2 plus 5 times 4. And that was the second row, second column. So I put it in the second row, second column of the answer matrix. All right, so now I've multiplied row 2 times each column of the second matrix. So I'm going to move on to the third row. Third row times the first column. The answer is going to go in row 3, column 1. So it's going to be 1 times 1 plus 7 times 3. And then my row 1, 7 times my column 2, 4. And I have 1 times 2 plus 7 times 4. And then I just simplify all this. So that's going to be -5. -8 plus 2 is -6. 1 plus 15 is 16. 2 plus 20. And 1 plus 21. And 2 plus 28 is 30. So that's how you multiply two matrices. Matrices are usually named with a capital letter. Vectors are usually named with a bold lowercase letter, or actually uppercase sometimes too. But what's important is that it's bold or that you put an arrow on top of it. So a matrix name is not bold, but a vector name is. So this X here is bold, or I could write this as X with an arrow on it. Your textbook does use bold letters, but when I'm writing on the board, I'll use the arrow because I don't want to like spend 10 minutes bolding a letter. All right, so a linear system is a system of the form x prime is ax plus by, y prime is cx plus dy. So it's called linear because your x and your y all just have like first power exponents. So you can write a linear system much more efficiently if you use vector and matrix notation. So A is a 2 by 2 coefficient matrix, A, B, C, D. Bold Y, that's going to represent the column vector of dependent variables, X and Y. So let's see what happens if I multiply A times Y, right? I have A, B, C, D times X, Y. First, let's make sure we can multiply them. This is a 2 by 2. This is a 2 by 1. My inner dimensions match, so I'm allowed to multiply these. And what's my result going to be? 2 by 1. Okay, so 2 rows, 1 column. So I'm going to multiply first row, first column, and I'm going to get AX plus BY. And then second row, first column, and I have CX plus DY, right? Which is our system. That was our original system. So that means that I can rewrite this system, X prime, Y prime, as the matrix A, B, C, D times the vector X, Y. Of course. A is the matrix. Yeah, I shouldn't have bolded that. Okay. The matrix doesn't get bolded. Only vectors are bolded. The arrows, yeah. Yeah. So you have your choice, and your book will go back and forth. It takes some like practice reading. Like I find it helpful to think of something bold as a drop-down menu. Like whenever you see something bold, you have to be like, oh yeah, there's a bunch of stuff there. So you can either write y prime with an arrow equals a times y with an arrow, or like when you see that, for a long time, I just had to translate that into x prime, y prime equals a, b, c, d times x, y. Right. So just translate it for as long as you need to until you start to be able to see one as the other. So we've talked about the harmonic oscillator, this mass on a spring, and it had the equation my double prime plus by prime plus ky equals 0. M was mass, b was the damping force, and k is the spring constant. So we can translate this to a system because a sliding mass on a spring has both a position and a velocity. So I can rewrite this as y prime equals v, and v prime equals, because v prime is really y double prime, you just solve for y double prime and you get that. So that's one thing that we use linear systems for, is the harmonic oscillator. But we can also use linear systems to model much more interesting things like love affairs. Okay, so Romeo is in love with Juliet, but in this story, Juliet is a fickle lover. So the more Romeo loves her, the more Juliet wants to run away and hide. But when Romeo gets discouraged and backs off, Juliet finds him strangely attractive. But Romeo tends to echo her. He warms up when she loves him and grows cold when she is uninterested. So we're going to try to model this with a linear system. Okay, so R is going to represent Romeo's love-hate for Juliet, and J represents Juliet's love or hate for Romeo. So positive values of R and J are going to be love, negative values are going to be hate.
What are the units on this?
Hearts. All right, so we're going to write a system of differential equations that shows how their feelings change. Okay, so we need an R prime and a J prime. Okay, so let's think about Juliet first, because we started our description with Juliet. So the more Romeo loves her, the more she wants to run away and hide. So when Romeo's feelings are positive, Juliet's feelings are decreasing. Okay, so we're going to take the opposite of Romeo's feelings. All right, and when Romeo gets discouraged, so like if he's backing off, his feelings are cooling, then Juliet likes him again, right? So if Romeo's feelings were negative, we have a negative here that's going to make Juliet's feelings actually become positive. Her feelings will grow. All right, but Romeo echoes Juliet. So he warms up when she loves him and grows cold when she hates him. So we're just going to put a positive J here. So when Juliet's feelings are positive, Romeo's feelings grow. Does that make sense? So this is most of what your project is about. It's called The Arc of a Love Affair, and you're going to analyze several different Romeo and Juliet situations. So this particular scenario, we don't have any analytic methods just yet, but we can make a direction field and a phase portrait with a computer, like I did here. So what does this picture tell us about the fate of Romeo and Juliet's love affair? They fall in and out of love over and over again. Yeah. So here, Romeo and Juliet, the first quadrant, they both have positive feelings, right? So they're in love, right? 25% of the time. right? And then 25% of the time, they hate each other. And then the other 50% of the time, one's in love and the other hates it, hates the other. All right, so that's it for our intro to 3.1. You're gonna do some activities. I'm gonna save like maybe 30 minutes to do the demo for the next lesson.